I agree. So I'm asking you to do two things. Sketch a graph with labels and an answer with units. Tom, you want to put a graph up there? Sure. Awesome. So Tom's putting your graph up there for you. And notice how Tom is labeling the vertical and the horizontal axes. Okay? And notice how Tom is putting numbers on the vertical and horizontal axes. Okay, all of this is part of annotating. He's doing a great job so far. Okay? Thank you, Tom. So there is what's happening for our 3-hour trip. How many times have we looked at scenarios almost like this, almost identical? A ton, right? We always kind of go back in motion when we kind of start to introduce things, and I do that because you're familiar with motion. I already heard a couple of answers from a couple of tables. So, excluding the front two tables, can somebody else give me the answer to this question? How far are you from home at the end of your trip? Right. 105 miles. Right? How'd you get that? Okay. So Ryan's saying he multiplied 3 times 35. So what did Ryan do? Let's get really calculus-y about this, so to speak. Awesome, Tyler. The area under the curve. Okay, and for this chapter, we're really going to get picky about writing and expressing things using calculus notation, because you're actually graded on this. You're actually graded on all of the pieces that go into expressing things like this in calculus notation. So what am I going to need to express this in calculus notation?
Integral.
We need an integral. Okay, what am I going to else? What else goes along with that integral?
Equation. 0 to 3.
Okay, a lower bound of 0 and an upper bound of 3. And what else?
Equation.
An equation. What is this equation? Yeah, right. It's y equals 35 or f of x equals 35. And what else am I going to need?
dx.
Okay, and it's a dx because that's the horizontal axis, right? Considering,
dt.
yeah, a good comment, Tom. Considering this is motion, I think a dt would be most appropriate. Although I would say a dx wouldn't be wrong. And what does this equal? What are we calculating?
105.
The answer is definitely 105. And the units are miles. You got all that
Distance.
correct. Yeah, are we calculating distance or displacement?
Displacement.
We are definitely calculating displacement. Okay, when we talk about, and somebody already said it, they said that represents the area under this function. Okay, because we end up getting 35 times 3 minus 35 times 0. And we have to acknowledge the fact that if that area represents a movement over time, it represents how much we've moved over time, that is our displacement. It does not account for whether we've stopped, turned around. It doesn't account for any of that. It just looks at the beginning and the end. Okay, so that is definitely our displacement. But Some people answer distance, and today's focus is really to kind of distinguish when we're calculating distance and when we're calculating displacement. In this case, what can you tell me about the distance?
The same as this.
And Tyler's saying the distance is the same as displacement. He's correct. Why is it the same in this situation? Exactly, Carly. Since it's all positive, it's all above the x-axis, so we're looking at that region being all positive. Okay, so displacement is a measurement from where you ended to back to where you began. Distance is kind of looking at your odometer. Okay, so we're going to kind of switch this up a little bit. We're going to take a similar scenario on this next page. Okay, so we're looking at this concept of integration for motion problems, and we've looked at this. Isn't the first time we've looked at it. We've looked at this before. So we travel 35 miles per hour in a straight line. So there's that graph you came up with just moments ago. Okay, and being able to articulate that is that represents our displacement. Then come up with what the position graph looks like. Okay, you know, the answer to problem 1 is obvious, but it does serve as a nice basis here for understanding the integral as that net change, as that displacement. Okay. If we end up 105 miles from home, we kind of talked about it on that last page. In calculus speak, we're looking at the definite integral over 3 hours. And we know that that is our displacement. Oops. What does the displacement graph look like? Talk at your table and come up with what that displacement graph looks like. Awesome.
No.
Exactly it. Excellent. Nice. That's awesome. One thing I wish we were able to do is I wish they had recommended drawing policy. Draw a straight line. So Kaylee's gonna share her graph with us. And what I see at your tables looks great. There it is. Kaylee, how did you know that that was a straight line instead of a curve? Okay, awesome. So we know we're gaining the same amount of displacement for every hour traveled. If we look at this, what's another way of determining that we definitely have a straight line here? We definitely have a straight line here instead of a curve. How would we know, kind of in a calculus sense, maybe?
The thing next to the integral, the 35, there's no t next to it.
Okay, so what if we kind of treated this as not a definite integral, but an antiderivative? We would end up with what?
35x.
Yeah. Or since we're integrating with respect to time, we're going to just change that variable to t, but it means exactly the same thing. And this is definitely a linear equation. So if we just treat that function, that velocity function, as an antiderivative instead of a definite integral with upper and lower bounds, we can see that that becomes a linear function. So we know we need to draw a line there. And there's lots of other ways to look at it. We can look at a constant as x to the 0, and we know integration bumps up that power to x to the 1 power. So we can look at it a bunch of different ways. So we're going to switch this up a little bit. We're going to continue to go 35 miles an hour. We're going to continue to drive for 3 hours. But instead of driving in the same direction for 3 hours, we're going to travel at 35 miles an hour in a straight line for 3 hours, but at the end of the trip, we're going to end up back home. What did we do in that 3-hour interval? Well, we're going to travel in a straight line. So we went out and back. Okay, yeah, but we had basically made a round trip, right? Okay, so at your table, come up with what the velocity function looks like. Okay? Check something. Remember, we're going at a constant speed, not slowing down, not speeding up. What does that look like? And in drawing that, maybe you want to ask yourself, what's my displacement? That might help. Awesome.
Can't do it anymore.
Carly, can I have you put that
Can't do
up
it.
on the screen?
So you can do
I see a couple of graphs that
it.
look a lot like what we started the hour with. That's not exactly the case. We've got to do something in this trip. What do we have to do in this trip? Remember, our speed is not changing. Awesome. There it is. Thank you, Carly. Why does the graph of the velocity have to look like that?
The position matters.
Because calculus. Awesome. Exactly, Alex. We've got to end in the same spot that we began, which means maybe we need to talk about this a little bit backwards, but our displacement has to equal how much? 0. Okay, we started at home and we ended at home. Which means, what is true about those two regions if we took the integral? They're equal, and one of them is negative. So how do I integrate this? If I want to put this into a calculus problem, and I would say, with these kind of numbers, if you made this a geometry problem, that would be awesome. Totally legal on tests, by the way. But if I had to write, because a lot of what we're being graded on in Chapter 7 is setting up the integral. In fact, they grade that more than they actually grade the correctness of the answer. So the setup might be worth 4 or 5 points. The answer might be worth a point. Okay? So I got my point for my correct answer with units, but I want to go after the 4 or 5 points with the correct setup. What would the integral look like? Discuss that at your table. What is the integral going to look like? What are my limits? What is the function I'm going to put in? And here I say, can I do this with one integral?
And then turn around and go back.
Okay, can I have you put that up there?
Just like this.
Uh-huh. We could also tell the story chronologically and put that out front, but it doesn't matter.
Wait,
But I agree with Tyler's comment.
okay.
I mean, if you look at the functions. Do we have one function over this 3-hour time? Ask yourself that.
No.
Awesome. So what needs to happen from a calculus standpoint to get the setup correct? Awesome. All right. So, what are our thoughts with what's up on the board?
Good second.
Okay, we've got a comment about an absolute value. Absolute value makes values what? Positive. Do we need all positive values in this situation?
No.
Nope. We definitely need a negative value. Which one's going to give us our negative value?
Or second one.
1.5 to 3.
Okay, 1.5 to 3. What is that function from 1.5 to 3?
Negative 35.
Is that what we have in our integral?
No, that's 35.
Okay, yeah, we definitely need to appropriately represent that function. Tom, could you hop up there and just put that negative sign there? Awesome, thank you, Tom. Okay, so we have a positive function for the first half of the trip that represents us driving how? Yeah, forward, away from home, and then the last half of the trip, what are we doing?
Turn around.
We turned around, so now our car is pointing in the opposite direction as coming back. And we ended up starting where we began, or ending where we began. And I noticed some of you have already jumped ahead here, which is awesome. Okay? And what does this position graph look like? So we notice what we're dealing with is a lot of piecewise functions, right? A lot of functions that have sharp corners, cusps, or jumps, gaps. What does that position function look like? Riley or Luke? No.
No. No.
Sure. Thank you, Luke. Appreciate it.
Yours, the Jake Berry's right next to it. The exact, it was almost the exact same picture.
So,
Yeah.
thank you. So a couple of questions. Does that represent zero displacement? Yeah, where's my beginning point?
Zero.
Zero. Where's my ending point?
Zero.
Zero. Zero displacement. 0 minus 0 is 0. What is this point? Do we know where this point is?
It's the turning point.
It is. It's where we turned around. We know it's how much time into the trip.
1.5.
We know it occurs halfway through the trip, 1.5. How far away are we? I agree. We are 52.5 miles away, right? We're as far away as we're gonna get, okay? We're turning around, we've covered half our distance out. Notice I'm saying distance for a reason. And then we're covering half our distance on the way back, okay? So our displacement, 0. If I look down at my car, and let's say when I got in the car, how many people in the car have a trip odometer that you can zero out, right? Okay, like I zero mine out every time I get an oil change, then I know when I need my next oil change. If I zero that out, and I start on this trip, go out, come back home, will my odometer read 0?
No.
What's it gonna read?
105.
105. But my displacement is 0. What is my odometer reading?
Distance.
Distance traveled. So there's my odometer, or my trip odometer, or whatever you want to call it. Odometer. There we go. Okay. So if the above expression, I'm just going to rewrite the above expression. Wait a minute, I forgot a T there. If that represents 0, then what can we write using calculus to represent 105? Okay, where do I need my absolute value?
On the negative.
Okay, so Nick is saying same thing. And that's a plus sign, just my sloppy handwriting. But we need an absolute value so that this becomes a positive movement. Do you know that you can actually put absolute value right onto your calculator? When you do an F-int. Okay, if you don't know how to do that, let me know, I'll show you. Okay. So our displacement is our actual real functions that we have shown graphically. Our distance is doing what if we have part of that function that shows a negative region? What do we have to do with that function? Put an absolute value on it so we can get additional distance accumulated, basically. Okay? How are we doing so far? Doing okay? Yep. Okay. Actually, one last thing before we leave this, just to kind of, we looked at this numerically, we looked at it analytically, in other words, we're setting up the actual calculus. We probably could just benefit from a quick graphical. So that's what we had up above. I'm just copying what we had up above. You don't have to copy that if you don't want to. But graphically, representing distance traveled is doing what to this graph? Yeah, taking this and taking the absolute value just means putting it back in the first quadrant, putting it back above that x-axis. So we now have that graphically, which is going to help you with the next 2 pages. Next 2 pages. Okay? So looking at that, could we have put the absolute value around everything? if we wanted to, and boiled it down to one, integral. We could have, it would be just as correct as what we have written. Okay, so we're just dealing with this basic, constant function. Let's try to apply this then to a function that's a little more, advanced. So here's our scenario. We've got a senior citizen taking a walk. So we look at the senior citizen's velocity here. And let's just tell a little story here. What happens in the first part of the senior citizen's walk to their velocity? Their velocity does what? From here to here? Goes up, right? They're speeding up. They're just starting their walk. They got a lot of energy. So maybe they can go faster and faster and faster, and then they reach a point here where their velocity starts to do what? Slow down. Maybe they're well into the walk. They're getting a little tired, walking a little slower. What happens here? They turn around. Yeah. So they walk a little slower here. They walk fast here. They turn around here, and they start
Getting faster.
Yeah, they start getting faster, but coming back home. Do they make it all the way home? How do you know they don't make it all the way home? The areas aren't the same, ladies. So when we look at this area, this represents what? Yeah, that's our positive displacement. They're walking away from where they started. And this area represents what? They're walking back, okay? So this is the walking back. And you mentioned something I thought was really important. And that is, do we make it all the way back to where we started? No, okay? And you know that because why?
Areas are different.
The areas are different, exactly. We have more positive area, which means we walked away a greater distance than we walked back. Can we see that here? We walk away a greater distance than we walk back. Okay, because we didn't make it all the way back home. Okay, we didn't make it all the way back. If this is our starting point, we didn't make it all the way back. So, did Harold turn around? What time? At 4 hours, or t equals 4. All right, let's take a look at the calculus behind this now. Go ahead and set up what Harold's displacement is. We know displacement is integrating the velocity graph. Okay, and what is Harold's distance traveled? Okay, so the appropriate setup there. So when talking about the displacement, next putting up the displacement function. You can get out of his own shadow. I know it's tough. so we're looking for proper setup. Do we have an upper lower bound? Do we have an integration sign? Do we have our differential or dx dt at the end of our integration expression? All of those things are worth points. If any of them are missing, we start to lose points. Okay? Awesome. Good catch on the DTs. Super. Okay. Okay, so a couple of things. Just from setup standpoint, College Board is going to want to see brackets here and here because we have a plus sign. They want that whole function capped in brackets. Okay? And so, likewise, then this whole thing would be capped in brackets. It's just a minor thing. Now, is that the displacement? Remember, displacement is, I have some positive regions and I have some negative regions. Do I have some positive regions and negative regions?
Yeah.
Yes, I do. We're good to go. Okay, I've got a positive region here and a negative region here. Looking at the function above, I'm not going to scroll back up, but looking at the function above, could I have written this as one integral?
Yeah.
I could have. What would that integral look like? This is correct. This will get you full points. But if I wrote this as one integral, what would my limits be? What would my lower?
0, 5.
0 to 5. And then I can just put my function in. Minus 0.5 x minus 2 squared plus 2 dt. Okay, I can actually just do that. Why can I do that? Why do I not have to split it up for displacement?
Because the displacement doesn't actually go.
It's one function. Will I get a negative region as I travel from 4 to 5? I will. Exactly. I will get a negative region as I travel from 4 to 5. As that goes below the axis, I will start to reduce my net area. So the idea of net area here, which is what displacement is, the idea of net area here is the reason why we can write it as one integral. What about the distance traveled? Can I write that as one integral?
No.
I have to do that as 2. So I have to use this approach here. And then what do I need? So I'm actually just going to take this whole thing.
Absolutely.
Yeah, I'm going to need an absolute value. So let's see if I can make this happen here. I want to group this and copy paste. Okay, that was not what I copy paste. There we go. So I have this, and where do I need my absolute value? On the 4 to 5, exactly. Now, here's a question. If I just use this one down here and put absolute value around everything, would that be okay?
Yeah.
Because isn't the positive stuff going to stay positive anyway?
No.
Yeah, on absolute value. So I really could take this whole thing and just put absolute value around that whole thing. So I could have done 0 to 5 of minus 0.5 x minus 2 squared plus 2 dt. And I could have come over here and said, I'm just going to put the absolute value across this whole thing. My positive will stay positive. My negative will flip positive. So long story short, if I want displacement, and if I want distance traveled, what do I need to have with my distance traveled?
Absolutely.
Absolute value, exactly. So anytime you see a distance traveled problem, you're gonna take the absolute value of the function. Just take a second with your table, and I would like you to graph the distance traveled function. Looking at back up at the original graph. What are we gonna change on that original graph to give me a distance traveled graph? How's that gonna look? Really close. There you go. Can you put that up there? Yep, totally. Lots of good distance traveled graphs. Looks really good. Close. Just that little thing that definitely has to have a curve to it. Question is, how does the curve need to look? Awesome. Okay. So we gotta take that little fin of a curve. It's gonna be piecewise. Okay. And the piecewise is gonna we really see that when we write it as two separate integrals. It's gonna be piecewise. Okay. But at that turnaround point, we need a little fin coming up. Now that little fin has got to go just as high as it went low. So did it go all the way to the peak? Did this fin go all the way to the peak? On the did it go down that far? Did it go all the way down to 2? It did go to -2? 2.5? It went all the way, so it went all the way down to 2.5. Okay, so we got to make sure that this goes all the way down. So if this goes all the way down to 2.5, it should go all the way up to 2.5. We can fudge that. No biggie. We'll just do this. There we go. Okay, we just got to make sure it goes all the way up as far as it went down to represent the absolute value of that function. Does that make sense? Okay, the last 2 frames are old free response questions. And we're not going to do the whole question, okay? And these are both calculator questions because we've done a lot kind of without a calculator so far. But for this one, all I want you to do is part B and part C. Okay. I don't think I actually, I didn't put that in there. But I just want you to do those 2. Okay, here's the function. Once you have the answer, let me know. And then the last page, again, I just want you to do one part. I think it's the last part. Again, with your calculator. So this is just working on your F-ins. Okay? So if you look at your table, let me know the answer. And when you have the answer, I'll give you a few minutes to get started on the website.
I'll see.
That's what I
Yeah. No. No.
Sine of t squared. So to make sure the squared is inside the brackets. Make sure you're in radian mode.
Part B.
It's 14 by 14, level 30. You want me to change the color?
Distance travel, that is the displacement, okay? So we have to add to that the initial position. Okay? And the initial position is 5. Okay? We'll go over the answers first thing tomorrow for those two problems. For chapter 6, when you are finished with web science.
I think I have one left.
Okay, and you done that. Look at that review sheet.
Okay.
Okay, and then let me know when you want to schedule it anytime.
Okay. And then there's one part of